We spent a couple of days looking at electric fields, the shape of electric fields, the direction of electric fields, and calculations involving electric fields, including when we have one charge or two charges causing those electric fields. I want to real briefly go through that again here today, just real briefly, and then extend that to a different scenario involving electric fields, come up with a new shape and a new equation that describes that new scenario. If we have an electric field that is caused by really anything, including the non-uniform field that we have seen up until today. That's a non-uniform field because the field lines aren't parallel. It's showing that the field is different depending upon location. Or if we have a uniform electric field, this is new today, a uniform electric field where the field lines are parallel because it's between two parallel metal plates or something that's like parallel metal plates. Either one. We're allowed to use the experiencer equation, E is equal to F over Q. It's sometimes what I call the universal equation. We're allowed to use this experiencer equation no matter what, as long as we have information about the experiencer. Doesn't matter what kind of field we have. The second equation that we learned last week for electric fields, the producer equation, is, however, not valid in this new situation over here. It's still valid over here. It's valid for a non-uniform electric field. And that's what we got last week. But now today, with these parallel plates, we have a uniform electric field. It's not valid there, no matter what. It's only valid in the non-uniform field. In order to describe this uniform electric field, remember, non-uniform electric field, this equation is good for. Uniform electric field, this equation is not good for. In order to describe the uniform electric field that we see on the right-hand side there, we need a new equation. The new equation, we'll also call it a producer equation, but this is our producer for a uniform field equation versus our old producer equation, which is the producer non-uniform field equation. The new one, the producer equation for parallel plates, is E is equal to delta V over delta D. E is electric field, of course. Delta D is not how far a charge has moved. It's not where a charge is in between the plates. Delta D is simply the distance between the plates. The distance is between the plates. It has to be. Like mathematically, let's just think about that for a second. If delta D was where the charge was, then where the charge was would affect the field strength. And it wouldn't be a uniform field then. It wouldn't be a constant field if where the charge was affected that field. Delta V stands for something called the potential difference. It's measured in volts, and I'll give you some more detail on that later in the next couple of days, but it is related to the energy. So there's a relationship between potential difference and energy. If you take the difference in potential between the two plates, delta V, and divide it by the distance between the plates, then you get the electric field strength. Now up here, we'd say the electric field is newtons per coulomb. Right here, we'd say it's newtons per coulomb. Right here, we'd say, anybody? Volts per meter, yeah. But in the end, that doesn't even mess you up. Just like we had kilograms meters per second for momentum and newton seconds for momentum, we can have newtons per coulomb and volts per meter for the electric field. It's no big deal. It's the same thing. You guys know what a Venn diagram is? Yeah? Yeah, 2 circles, sometimes 3 circles, but sometimes 44 circles.
Oh,
We're just going to draw 2. Okay, it gets a little bit more complicated when you have 44 of them, but you could. Let's write out our 3 equations. This is our producer equation. Remember our old producer equation. This is our experiencer equation. This is our new producer equation. If I draw a circle around these 2 equations, sorry, that should have F over Q, right? If I draw a circle around those 2 equations, they would represent the field that is non-uniform, the field that's not constant. Now, the first one describes the field if we know something about what caused the field. The second one is, well, if we know something about what experiences the field. But they're both valid when we have a non-uniform field like this. The second list, or the second circle, encompasses a uniform electric field. The bottom equation describes if we know something about the plates themselves, and then the middle one, of course, describes if we know something about what experiences that field. So whenever we have this non-uniform field, let's use what's circled in blue, either one of those, depending upon what we're given. And whenever we have what you see here in the red diagram, a uniform field, let's use what's circled in red. Just depends on what we have given to us, which one of the 2 we use. Yeah, cool. Oh, sorry. Yeah, it should be delta V over delta D. Yeah, thank you. Now, sometimes we look at something like this and say, like, well, okay, yeah, that's great. 2 parallel plates. When do we really have 2 parallel plates? Like, when do we really, in real life, have this uniform electric field? Like, people can see where we have, you could have a charge, a balloon that's charged, and the non-uniform field that surrounds that balloon. But when do we have, in real life, a uniform field? Like, it seems like such an artificial construct to have 2 charged metal plates with a field between them, right? You know what? Oftentimes it is. Oftentimes it is artificial. But there are situations where we would have something like this in real life. For instance, tell me when you recognize this.
Train tracks.
No.
Bumper cars.
Bumper cars. Yeah. The top plate, you got this metal roof that's charged. I don't know whether it's positive or negative. I don't know which way the current goes. But it's charged. The bottom plate is charged. And then this metal rod that goes up from the car completes the circuit. That's a uniform electric field in there. If you were to take a balloon and rub it against your hair and charge that balloon and put it in that uniform electric field, then you would find either the balloon would accelerate downward due to the electric field or accelerate upward due to the electric field, depending upon which way the electric field went. In this case, it would be going down this way, but we could easily have the top plate negative and the bottom plate positive, which would mean it would go opposite to that. Okay? Uniform electric field, field lines parallel. Okay? That's exactly what we see over here. Now, here's another situation where it's a very good approximation of a uniform electric field. Tell me when you start recognizing this. This is a negatively charged cloud, or the bottom of it's negatively charged. The Earth develops a separation of charge so that the top of it is positive. Like, it's not quite parallel because the Earth is round, right? But over a localized area, the Earth is relatively flat, right? When you look outside in the field, it doesn't look to be curved. It looks to be flat. So over a localized area, these are 2 parallel plates. In this case, however, we'd have the field lines pointing up from positive to negative upwards. Still a uniform electric field, though, right? We could still describe this situation by using either one of these equations that are circled in red. The experiencer equation, if I had something here to be experiencing that field, or the uniform field producer equation, delta V over delta D, to describe the field given the distance between the cloud and the ground and the potential difference. Now, I want to point out one little thing that is not significant to us. I just want to point out in case you happen to see a picture labeled like this. Around the edges of these parallel plates, you actually have a non-uniform field. It actually curves out like this. So it's not quite uniform at the edges, but the only place you'll actually have to analyze it will be in the middle, where it is a uniform field. So if you see parallel plates or something like that, it's safe enough to use my uniform field equations, the red ones, even though at the edges it's not uniform. Does that make sense? You know what, honestly, most times you don't even see it drawn like this. Most times those aren't even drawn in, but technically it is there. So just in case you see it, don't get thrown off by it. Okay, let's do an example. So example number 4 says a potential difference of 20 volts exists between these two charged parallel plates that are 3 centimeters apart. Top plate is a negative and the bottom plate is positive. Let's draw this out here first. Here's my top plate is negative, bottom plate is positive. We can draw these field lines. They're parallel to each other and pointing upwards because they always point away from positive and toward the negative. If I was to put a positive charge in there, it would experience a force with the field. Remember, the force, I'm positive, the force is with the field. That's why the field is upwards, because that's the way that a positive particle would move if placed in the field. Let's find the magnitude of the field here. We know it's upward already. Let's find its magnitude. We use the producer equation for parallel plates. Delta V over delta D. We're going to say 20 volts divided by 0.030 meters. And I think that gives me 66.66667. You can say volts per meter, or we could say newtons per coulomb. Either one of those works. Is it 666? Okay. Sorry. 66.67 volts per meter, or we'll just say 667 volts per meter as a rounded value. Okay, easy enough, right? Make sure you don't use your producer equation for non-uniform fields. E is equal to kq over r squared. Now I want to find the force experienced. Remember, it's a uniform field. I'm allowed to use this equation or the other equation, the experiencer equation, F over Q. So F is equal to Q times E. So we're going to say, what is it, 1.6 times 10 to the minus 19 times 666.667. That gives me a force of 1.0666 times 10 to the minus 16 newtons, which we want to find the acceleration. All we're going to do is take that force and divide it by the mass. We're allowed to use this whenever we want, right? As long as we have a force and a mass. So you know the force, you just found that, you know the mass, let's calculate that. Now, here's what's homework, guys. Worksheet number 8, I believe it's 10, 11, and 12. But it's finishing off that worksheet anyways. As I say, I think it's 10, 11, and 12, 3 questions. Let's get those done for tomorrow. We'll check them over. We're good to go.